Hello and welcome back to our plasma physics course. This is lecture 12, as explicitly stated on top of the page. And we're going to pick up where we left in lecture 11. That is, we're going to continue the derivation of fluid equations from, I'm going to say, physical intuition. Even though we're not really guessing, we're doing the physics right, but we're doing the physics in one of the two ways this could be done. That is, we're starting from a fluid element and looking at what happens to that fluid element rather than starting from the single particle description and integrating some way over the particles, whatever we will need to do. And part of the reason, just in case that was not clear in lecture 11, is that we didn't really go and write an equation for the distribution function, which is what we will need to integrate. Therefore, either we go through the process of kinetic theory and then get to the fluid equations, or we try to get the fluid equations in some other way, which is perfectly okay. That's the way fluid equations, it's a normal way to derive fluid equations. That's the way they were first derived in fluid dynamics. Many fluid dynamics courses start this way without ever talking about single particles. Okay, done with the introduction. And let me remind you where we were. We were talking about conservation of mass. That's the first thing we need to conserve. Now you may think, well, where we're looking at nuclear fusion, really mass isn't conserved. We'll take care of that. For now, we're looking at the fluid element, and we're not worrying about that part. We're going to write macroscopic equations for the conservation of single species. And as we proceed, we'll see that we're actually going to look at this as a system of two species. So we're going to write a set of two fluid equations, as was already announced. Where we were was here, that the total derivative with respect to time of the number of particles in a fluid element was equal to the volume of the element that we call delta V, if you remember, times the derivative of the density plus n times the derivative of the velocity in the x direction, which we call the u sub x, over x plus n derivative of the y component of the velocity of the fluid element with respect to y plus n derivative of the z component of the velocity with respect to z, which we can summarize as volume times dn over dt plus n divergence of u, and this whole thing needs to be equal to 0 because particles are conserved. That's what we've been saying. Let me just put this in as a reminder. This capital N is the number of particles in the fluid elements. Number of, let me type it. Somehow I made an error that's not appearing on my screen. I hope it's actually there. Looks like I'm maybe having some connection problems. Great. Well, anyway, that's the number of particles in the fluid element. Oh, I see what happened. Okay. Little pause and I'll fix it. We always have technical problems, right? All right. Now that I've magically made finally all the things that were supposed to be on the page appear, I'm ready for the last step in this derivation. I would like to remind you of something before I do that. And in particular, I would like to remind you of the fact that we are using a Lagrange description of the plasma, of the fluid element, really. That means that we are identifying a fluid element and we're following it and figuring out what happens to it. Now, equations are, in general, but not always, more useful to us in the frame of reference of the lab, and that's what's called the Eulerian approach, where we set a system of coordinates, and we use that for describing our plasma. The reason why I mentioned that is that here we're going to have to take an additional step. We have this time derivative of the density. That's the Lagrangian derivative. We have to convert it to a Eulerian derivative. If you've never seen this before, we can do it in class. If you have, I'll just write the result. And I'm going to do my best to write it in a way that's reasonable or readable. Let's see, dn over dt, what happened here? Now, this derivative, and I'm going to type explicitly that this is Lagrangian. Make this a little bit smaller. That's going to be equal. This is not an equation in the sense that it's something we have to satisfy. This is exact. It's a transformation of coordinate, if you wish. This is going to be, again, equal in the Eulerian description of the plasma to the partial derivative of the density plus u dot grad n. And again, this is going to be the Eulerian description. And I'm going to make this a little bit smaller. There. If you have not seen this before, don't worry too terribly much. Now, the last step, just take it on faith. The last step in our derivation is to go back to our equation on top of the page. Let me call it equation 1. And observe that that equation needs to be equal to 0, and it needs to be satisfied for any fluid element. In other words, the volume of the fluid element is irrelevant to the equation. It's what's inside round brackets that needs to be 0. Then I'm just going to work on that, and I'm going to rewrite it as now in the Eulerian system, dn over dt partial plus u dot grad n plus n divergence of u equal to 0, which I can transform into the form that's more commonly used, the n over dt partial again, plus divergence of n times u equal to 0. And that is our continuity equation. Simple vector transformation. I'm going to guess that you've seen this before, but I can take u inside the divergence because I have the something like a scalar times a vector. And if I take the divergence of this product, n times u, I get exactly what I have on the left of the page. So that is my final version of the mass conservation equation. And I'm going to have the same identical expression for both ions and electrons. So what's going to change is that in general, the densities may be different. If I have, for instance, ions that are multiply charged, I'm going to have fewer ions to conserve quasi-neutrality. Say I have helium, then the ion has a charge of 2, then the density of the ions will be half of the density of the electrons. So the numbers will be different. The velocity of the ions will be different from the velocity of the electrons. But the form of the equation is going to be the same. And let me remind you one last time before we move on that here I'm talking about velocity, and what I mean is macroscopic velocity. It's not the velocity of a single electron. This is macroscopic velocity. I've been using v for the velocity of a single electron. Let me make this green. And it just decided to move by itself. Okay. Well, it moved to a good spot. All right, that was all for mass conservation. Are we done? Of course not. Now we may say the fun begins or continues, or it's never going to start, depending on how much you like these things. But what's going to happen next is that we're going to look at conservation of momentum. And we're going to proceed in the same manner. We are going to take a Lagrangian approach, look at a fluid element, and ask the question, how is the momentum of this fluid element changing? Figure it out and turn it into the Eulerian description. And this is go maybe a little faster. All I'm going to have to do really is to transform the derivatives as written above here. Let me perhaps put a box around this equation too, so that I emphasize that this is an important expression that we're going to need again. All right. How's this going to work? Well, we know from physics 1 that force is equal to mass times acceleration, but we really say, well, that's not how I like to write it. I mean, it's not wrong, but it's not like how I like to write it. I want to write this as the derivative of the momentum. I'm using P for momentum, which I'm going to use also for pressure. So this is going to be very confusing, but this is the only place where I'm going to use it. I'm going to make it disappear. Okay, then if this is true for a single particle, it's going to be true for a fluid element that's made up of a good number of particles, hopefully, at least. Therefore, what I'm going to say is that, well, I'm going to try to calculate the time derivative of the momentum in my system. And that's going to be equal to the net force or total force. And I'm just going to write force on the fluid element. Here, element. Well, then what we have to do is figure out what the expression of the momentum is and what the forces are. Let's start from the second piece. What could be the forces acting on a fluid element? Just taking a moment to start writing down, I would also like to give you a moment to think about it. So if you want to guess, pause the video here for a moment. And when you restart, I'm going to tell you. In no particular order, just as they come to mind or as they're listed in Professor Freiberg's book, which we're following for this part of our course, I'm going to have forces due to the electric field. I'm going to have to figure out what that is, but if there is an electric field, we know electric fields cause forces. Let's figure that out. Then I'm going to have forces due to the magnetic field. Again, I'll have to figure out what that is. We'll do it, of course. I'm going to have forces due to pressure, in particular pressure gradients. This may or may not be intuitive, but you know that if you have a pressure is a force divided by a surface. If I have a pressure on the side of my fluid element, that's going to exert a force. If there is a pressure on the opposite side, that's also going to exert a force. If the pressure is constant, the forces are going to be equal. Therefore, I'm going to have a net force only if there is spatial variation in the pressure. That is, if I have a gradient in the pressure. I'm giving away how I'm going to do this, but well, forgive me for the spoiler. And last, I'm going to have a collisional force, which is in practice the friction between ions and electrons. So if let's say I have a cloud of electrons that's not moving, and I make my plasma of ions and electrons, and I shoot the electrons and all in a beam, they're going to have collisions with the electrons, and they're going to drag them along. The ions are moving in a certain direction, the electrons are going to start moving in the same direction because of collisions. and vice versa. So that is what the collisional force means. Now that's going to give me terms such as viscosity and resistivity, in particular in the momentum equation. This is going to give me viscosity. Resistivity is going to come in for the equation for the, let's say in the Maxwell's equation, it's going to come in through Ohm's law. But viscosity is typically not very important. It may have an effect at the edge, but in general, we can pretty much throw it away. So what I'm going to have is just the collision between ions and electrons. If there was some additional viscosity due to dissipative effects, that will not appear here. All I'm going to have is the transfer momentum between the two species. Oh, I'm also throwing away the gravitational force, because in most plasmas for fusion applications, especially, this is not going to matter. It may be more important in systems like dusty plasmas. We know there is going to be a difference between the way a dusty plasma behaves in the space station or in a lab on the ground. It may be more, may have an importance, some effect in the magnetosphere, but let's keep it simple. It's going to be intuitive how to put it in. I'm not going to have it. Okay, then. First things first, I'm going to look at the momentum, and I'm going to look at the time derivative of the momentum, what's called in some cases or some books, including Friedberg's one, the inertial form, inertial force, not form. Okay, then, how do we write the left-hand side of our equation? Well, start with small fluid elements, or well, proper size fluid element. Could be made of electrons. Let's, in fact, focus on electrons for now, because we'll have to decide about signs for the electric and magnetic field terms. We can then redo the same exact thing for ions, which I'm not going to do. I'm just going to infer the results. Then we're going to have a fluid element that contains a certain number of electrons. Let me call it n sub e, which is going to be equal to the density of the electrons times the size of the fluid element. Then the average momentum for an electron in my fluid element is going to be given by the mass of the electron times the average velocity of the electrons, which is going to be the velocity of the fluid element. So it's going to be me times u sub e. And that immediately gives me the, let's make some space, total momentum of the fluid element is going to be really crazy. It's going to be given by n, number of electrons in my fluid element times e u e. Then its derivative let me write momentum one more time in here. That's going to be the derivative of this expression times u sub b times the number of particles, which is given by delta v times ne. And then I can take outside, for sure, the mass of the electrons. That doesn't depend on time, but also from conservation of mass, the product Ne times delta V, which is capital N sub E, is a constant. Its derivative with respect to time is 0. So that also comes out. And therefore, I get delta V times Me times Ne times the derivative of what's left, which is let's see, what do we have left? Just U sub E. Now let me write this underneath. The one on top is my Eulerian description. I'm going to transform this into the, I'm sorry, the one on top is the Lagrangian description. I'm going to transform this into the Eulerian one. The stuff outside the derivative is not affected by the transformation, and the derivative of the velocity becomes partial derivative plus U sub E dot grad, all applied to the quantity I'm taking the derivative of. That is, again, U sub E. Okay, that's the first term that we were trying to figure out. Now, let's follow our list of forces. The first force that we have is the electric field force. Let's see. Let me type this to keep things in good order. This is actually pretty easy. First of all, the electric field is going to have an effect because I have charged particles, and each electron is going to have a charge equal to minus C, the elementary charge. Then the total charge in my fluid element is going to be the charge of a single electron times the number of electrons. That is, let me call it Q sub E, is going to be equal to minus E times big N sub E. The electric field force, we are in a good position to calculate it. We know what that looks like. That's going to be equal to, oops, whatever charge I have, let's say Q, generic Q times the electric field itself. Therefore, for our system, this turns into Q sub E times E, which I can write replacing the expressions for NE and Q. Maybe a good idea to, these are not big results, but are things we're going to use here and there. So let's keep them in mind. Okay. What I have here is minus, that comes from here, E times NE, big NE, which is delta V times lowercase NE. I'm going to pull the delta V in front. At the end, I'm going to collect it like we did for the mass. Therefore, I get delta V times E times lowercase n sub E times the electric field. Now, where the electric field is not the electric field of a single particle, but is the electric field that's averaged, or not averaged, but smoothed out over long-range distances. Here is an important and subtle point. Each charged particle in my system is going to generate an electric field. And each other particle that comes close enough to the first particle is going to experience that electric field and therefore interact with the first particle. That interaction is what we described as Coulomb collisions. We spent some time talking about collisions. Over distances larger than the Debye length, I'm not going to see that individual charge, but I'm going to see smoother effect, a long-range electric field, which could in part be applied from the outside, but in part be determined by the response of the plasma to whatever is happening to the plasma. And that is the one I'm going to use to figure out what is happening to a fluid element. It's not the field due to a single particle, but it's the long-range electric field. And other minor spoiler, I'm going, of course, to do the same thing for magnetic field, for the magnetic field as well. Okay, so that's the force we were trying to find, maybe I should put little boxes around the things I'm going to use. You'll notice that there are no derivatives here, and therefore I don't have to worry about is this Lagrangian or Eulerian. Doesn't matter. I'm not taking derivatives. Derivatives are the place where I have to be careful about which treatment, which description I'm adopting for the plasma. Now let's separate this small section from the one for the next force, and let's go back and look at our list. The next force is the magnetic field force. So let's see what that is supposed to be. Just realize that even with the help of all these lines and automatically straight lines, my lines are never automatically straight. I mean, they're straight, but they're kind of leaning one way or the other. Anyway, magnetic field force. This is pretty much, I don't want to say trivial, but it's very simple to derive. We know how to write the Lorentz force for a single particle, or the force is Q times V cross B, where V is the velocity of the particle. For a collection of particles, I'm going to use, instead of the charge of a single particle, I'm going to use the charge of the fluid element, which we call Q sub E. I'm going to use the velocity of the fluid element, which is U sub B, and I'm going to cross it with the magnetic field, which is, again, going to be the long-range magnetic field. This may be a bit of a leap of faith. You may not exactly be clear what I'm doing, but you can convince yourself that this is the correct expression in two ways. You can think I'm going to sum over all my particles. Well, then what I'm going to have is the average velocity of the particles. The magnetic field, again, is the long-range magnetic field. I don't need to take care of any variations of that magnetic field while I look at my fluid element. That magnetic field is the same for all particles. And the total charge is just going to be the number of particles times the charge of a single particle. Okay, so what do we get then is this expression, which again does not have any derivatives, and now I'm using the expression I have there for Q sub E, which I'm going to express again in terms of density and elementary charge. That's going to give me delta V times E times N sub E times U sub E cross B. All right, we're doing great. This one wasn't too hard. What is going to happen next? Maybe a little bit more challenging, but it's not going to be too bad. Okay. What we have next going back to our list, is the pressure gradient force. This may surprise you, but there was actually some logic in the order that we used for our equations. Our forces, we kind of started from the easy ones, and we're working our way up to the ones that are a little bit more work. Okay, now I already said earlier in the same lecture that pressure exerts a force on a surface, but the fluid element really doesn't have a solid surface. Particles can come in and out. So that picture may be a little misleading or not so intuitive, but let's see what this looks like. If we look at the motion of individual particles, oops, that went badly. Individual particles in and out of our fluid element. My green thing here is my fluid element. My green fluid element, okay. Now let's look at our particles. Let's say a single particle now moves with some velocity. This position is going to be, oops, you just call it x minus delta x over 2, where delta x was the size of the fluid element in the x direction. And here I have x plus delta x over 2. That is the position of the fluid element in the x direction is the center of this box. And then I look at what happens on the two sides. And well, there are going to be 4 types of particles. I'm going to have particles on the left, 2 options, and particles on the right. I'm drawing 2. This is like a bit of a fat particle, but that's okay. It does happen. And I'm going to say, well, the velocity of each of these particles could be in any direction. What I'm concerned about here is the x component of that velocity, and that x component could be in could be 0, then the particle doesn't matter, or it could be in the box or out of the box. And these lines are supposed to be perpendicular to the surface of the box. And same thing here. Clearly not very good at this, if you hadn't figured that out yet. Now, for the momentum in the x direction, let me call it some total mass. Well, we do have the expression of the momentum, so I might as well just write the expression. That was delta V E, and then for the x direction, U sub EX, and which is of course in the x direction. Now, what is going to happen as particles move in and out? Let me call these velocities W. I'm going to call them all W, and I'm going to, except for the last one that I'm calling with a with a disaster. Sorry about that. W. All right. Where again I'm representing all the x component. Now, what I mean here is the following: that put an equal sign there. That is what we've been calling V. Well, I'm going to call it W. Well, V is going to be equal to the average velocity plus the deviation from the average velocity. The average velocity now is the velocity of the fluid element. The deviation from that velocity is what's going to tell me is this particle going to leave the fluid element or enter the fluid element. And that is what I need. If a particle moves with a velocity that's exactly equal to the velocity of the fluid element, it doesn't leave the fluid element, it doesn't cross the boundary. Those are the particles I'm concerned about here. Okay, now we're interested in what happens to the momentum of the fluid element as particles come in and out. And I encourage you to try to understand what each one of these four particles does before I tell you. Good moment to pause the video, go get a coffee and try to figure this out. Now, if you have resumed the restarted the video, you may have concluded that particles that are crossing the boundary on the right are causing a loss of momentum. Okay, this is hopefully obvious. You'll say, well, sure. If not, let's spend a moment on it. And we only need to do it on this side. It's going to be the opposite on the other side. Okay, what is happening here? The particle on top is moving faster than the average velocity of the particles in the fluid element. And then it goes away. So that means the total momentum of my particle, my fluid element, which was moving in the same direction. Didn't narrow, sorry. Is decreased. I'm taking away a particle that's moving faster than the average, then the average is going to decrease because I'm not taking away the particle that was moving slower than the average. On the other hand, the particle at the bottom is entering the fluid element, but it's moving in the wrong direction. It's moving, well, there's nothing wrong with it, but it's moving with the direction that's opposite with respect to the direction of the fluid element. And therefore, that particle is also going to make the average momentum of my fluid element decrease because I'm adding a particle that's moving slower than the average of my particles. Notice that the velocity v, I'm sorry, v may still actually be on the right. It's just that w is negative, pointing to the left. That is because my particle I'm looking at now is moving less quickly, more slowly than the average of the particles in the fluid element. Okay, then what happens for the other particles, the ones on the left? Well, the exact same thing with the opposite sign. And the reasoning is exactly the same. For the particle on top, I'm bringing in a particle that's moving faster than the average. That means the average is going to increase. For the particle at the bottom, I'm taking out a particle that's moving slower than the average. Therefore, the average is going to decrease. So that is what happens. And now we have to figure out how to put the pieces together. And okay, here we're not quite going to cheat, but we're going to invoke our understanding of what the distribution function was. Even though we did not write an evolution equation for the distribution function, we can still use it in trying to calculate how things move. Now, let's see if we can figure this out in the time we have left. Let's focus on the first particle on top. I'm going to call this particle 1. And this particle is going to carry some momentum out because it's exiting the fluid element. Now, how many particles are going to do that exact same thing? Now, let me type that. I'm worried about the particles leaving the fluid element with a specific velocity in Wx. Oops, let me put this in blue, sorry. I'm looking at particle 1. I said particles, I could have said electrons, since we're looking at electrons. That's going to be equal to my distribution function of the electrons, which is a position of r, and I can define it as a it's a function of the position r, a function of the velocity. I'm going to use it, express it in terms of w. Can always do that. And it's going to be the particles in that element of velocity space, so that around that velocity w sub x, and this multiplies the size of the surface delta x to delta y, and the whole thing is calculated at x plus delta x over 2 on the right hand side of the right side of my fluid element. Okay, now in general, each of these electrons is going to have a certain amount of momentum which is going to be equal to mass of the electron times the velocity of the electron. Notice that this is the total momentum, because in principle, I could say, well, that's going to take out momentum, or to be rigorous, I can to say that's going to take out, the particle is going to take out momentum in all the directions where it's carrying momentum. That the momentum of that particle is leaving my system. So I need the vector, not just the x component. And then I do the sum over all particles to obtain the total loss of momentum. And that's going to be, okay, the size of the surface I can take out of the integral delta x, I'm sorry, delta y delta z. Oh, I have x and y here. Sorry about that. It's the size of the fluid, or the surface of the fluid element that's perpendicular to the x direction. So that's delta y delta z. Okay, then I do the integral over my distribution function f sub e as a function of position, velocity, and time, that multiplies me times w, that's momentum of a particle, times wx, the velocity the particle has pointing outside of the fluid element, and this I'm going to integrate in delta w in dw, I'm sorry. But I'm going to integrate only on the particles of type 1, that is the particles with wx larger than 1, 0. Particles types 1. Now, I'm not going to redo it, but maybe you can try. I'm going to apply the same reasoning to particles of type 2 and say, well, I'm going to have a loss of momentum that's proportional to the momentum of each particle coming in with that negative velocity wx. How many particles I'm going to have? Well, I figure out in the same exact way. And what is going to be the total loss of momentum? I do the same integral just on particles with negative wx. Therefore, the loss of momentum for particles 2, let's put in quotation marks, Too many? Okay. That's going to be the same integral. Delta y times delta z. The size, my fluid element is a cube. The size is the same on the opposite side, times the integral of the distribution function, r function of r, w, and t, times the momentum of a single electron, times wx, and then I integrate in dw, and this I do for wx less than 0. Now, you see that the two integrals are the same. I'm just going to finish this integral and we'll pick up from here. I thought we would be easily done with this derivation in a single lecture, but I just take too long to do everything. Okay. Must be the old age. All right, jokes aside, total loss of momentum due to electrons 1 and 2, where remember 1 and 2 are not two individual particles, are one are electrons that are moving out with positive W, and 2 are electrons that are moving in with negative W. Sorry. That's just going to be the integral in blue over all W's of, let me put the delta x, sorry, delta y, delta z in front. Delta z times the integral over all W, all Wx, I'm sorry, of my distribution function the position, W and T, times ME times W times W X in the W. All right, we'll pick it up from here on the next lecture. Thank you, and we'll see you with the next video.